Yeah, you can type in the chat or sound wave. Okay. Any else? Waves. Okay. So there's no electricity circuit involved, right? No. Okay. Yeah. So up to that, someone just get started. Okay. I believe like generally we need to finish all the mechanics, including the rotational motion, just like we're going to cover today and next week, and the sound and wave. Okay. And electricity's electric field depends. They said they will release the details on the beginning of April. So we will discuss more at that moment. Okay. Yeah. All right. So the answer of the multiple choice. Let me find it out. First, I share that. Okay. Okay. Let's do the first. B A D A C B. Sorry, I have too much of that. Yeah, so that is just for the first. They split into different sections, right? Yeah, so that is the first 22 collections in. I was thinking, can I lay out columns and down? Okay. Okay, does this work? Energy. Okay. Number 9 is B, A, and C, A, B, C. Hold on. So problem number in 10. There's a problem like D. Or is D, A, Letter B here. $23 is D. 24 is D. All right. Any question we need to discuss here? Yeah, if you need to talk, you can just unmute yourself or turn on your videos, right? Okay, I get a question number 15. 15, Tuesday. You mean in which section? The first part or second part? Second. Okay. Oh, is that which two? Okay. Two toys car with different masses, original at rest, and pull apart by a string between them. Um, Okay, which one? So obviously that the linear momentum should conserve, and which one have the larger kinetic energy? Oh, actually, B is not correct. Yeah, number, change that. So both toys will require inquiry, and A is correct. It should be C. Right. Yeah. So basically that they should have um, the same amount of the linear momentum, but for the larger mass, um, the speed it should be smaller. So actually the kinetic energy is different. So you can consider we have a smaller speed, but after you square it and time the math, and actually they have a um, smaller energy. So the larger mass actually have a smaller the kinetic energy, right? Okay. Someone asked for uh, part 1, 7 and 9. Let's go back to that. Seven and 9. Okay, let's try this too. Okay, so we have a card of mass m slide across a patch of ice at a speed of v. One is a brake slot. Is this heat dry pavement and slide to a stop in the distant b. Coefficient of colliding frictions between the tire and the dry road is mu. So, okay, so first, if the car have a mass of 2m, it will have slide distance of, yeah, so you can use the work energies theorem. So the work done by the frictions to stop is equal to the loss of the kinetic energies, right? Yeah, so like try that to right here. Oh, here we go. Yeah, so use the work energy theorem. Okay, so the work done time d should equal to the change of the kinetic energy, right? V initial square. And this part is yeah, so you can find out that this one is mu mg d, right? Equal to half of the mv initial square, right? So you can find out this that depending on the masses, right? So it doesn't matter. So even you increase the mass and didn't change any for the d, right? So the mass is have no effect to the distance is skated. So B. Okay. All right. Number 9. Okay, number 9. A ball is thrown vertically upward with velocity v and initial kinetic energy is ek. So when halfway to the top of the flight, it has the velocity and the kinetic energy. Okay, all right. So we know the initial kinetic energy and we know the initial speed, and we want to find out what's happening halfway to the top. Number 9 here. Oh, you can picture in this way, since it's just travel halfway, right? So the potential energy has to be half of the total kinetic energy, right? So which means that half of the kinetic energy has been transferred into the potential energy. Oh, I mean the potential energy has been like just half of the total, right? So yeah, you can just using the energy to think about the fractions. So in that way, at the halfway, the ek should equal to half of the initial ek, right? Because the other half has been converted into the potential energy, right? Because the potential energy EP is proportional to the height, right? So it's just a half. Yeah. All right. Then in this way, we can get this result as half of the mv square at that moment. Or say this is half with the prime, right? This prime with prime equal to half of the mv initial square, right? So you just cancel off that. So the v prime should be, oh, sorry, just half of that. You just need another half, right? This half is part of the kinetic energy. So it should be vi root of 2. And yeah. All right, does that make sense? Yeah, we use energy to concern half of the potential energy, yeah, at the halfway, right? And which means that the other half has converted from the kinetic energy into the potential energy. Any other questions? Okay, last call. Any other questions in the homework? Nope. Okay, good. All right, let's go back to the last package. Let's finish up that first. All right. I believe we done most of that part. Yeah, we done this question, right? Okay. So next is rotational kinematics. Okay. All right. So this is a question. This is why we have this name like this is like the well, it's like study with the system, right? So for the system, they can have two type of motion. First is like a translational, which is every point move in the same direction and with the same speed. And then just yeah, obviously they should move in the same. It's like velocity, right? Otherwise, they will just take apart and cannot be a system at all, right? So they should move like together, right? But this is like from outside what we say for each point inside of the system. However, like inside of the system, they can also have a relatively motions, right? So it can be rotate. So this is the situation we discussed. So with some axis, so any point can rotate with this axis rotations with some like a yeah, they may have some like a rotational speed or say the like a uh, is usually defined as angular velocity, right? So any point actually can rotate with this axis pivot, and still any point can move with the same speed, like a translational. So this is like they can doing these two motion at the same time. Like this object, just like a wheel, right? Just like the wheel of the car. So the wheel is like rotate with the central axis. So every point is have the same angular velocity with this axis, right? And the wheel itself, like the car, is moving translationally, right? So yeah, so this is what going to happen with like a little bit complicated motion of the object. Previously, without consider about rotational motions, we already consider your object, the object we study as a point mass, right? We don't consider about the size or the shape of that. But when we consider about the rotational motion, we need to consider about the size of the object we study. Okay, the rotational kinematic, just a quick recap. Well, is you can find out the definition for different, the terminology is pretty similar to that of the translational motions, right? It just have a angular step adding in front. It will have an angular displacement, right? So just like for a certain of times, how much angle is rotate, you can just picture in that way. Yeah. Yeah. So here using delta is equal to theta minus theta naught. Yeah, you can just picture we still have a reference point. So um, like, yeah. So we will have like a starting angle. So this is the starting angle. We using that. This is the direction of like a reference, right? We're taking that angle as the reference, and then we rotate counterclockwise into a new locations. So that is it's like yeah. So total is will be like a well, sorry. Yeah, we're starting from here and we define initial is theta naught, and now is has been rotated to a new location like a theta, right? So the angle is rotate will be the delta theta, will be the displacement, right? Yeah, just like initially we have a point uh, here, and then it's starting from the location P naught, right? So that P naught is X naught, and then we move to that direction. You have a P1, so we see the displacement, and this is X, so it'll be X minus X naught, right? So this is what would happen to define the displacement in the linear cases. But for a rotational cases, it's pretty much similar. We're choosing one as a reference point. Okay. Yeah. We follow the same definition as the angles. So we know that if you define an angle in the geometries, if you rotate, just this is counterclockwise, right? But in your hand, it should be this way. Yeah, because when you go counterclockwise, we define the angle is positive, right? But if you go this way, clockwise, we define that as a negative angles, right? All right, so for the angles, we have a three common unit we're going to use, like degree, radians, and revolutions. Revolution just like when they finish one complete circle, go back to initial point. We call this the angle is rotate is 1 revolutions, or it should be a what 360 degree, right? Or in radian is 2 pi radian. So you just need to know about the conversion among the three. So 360 degree should equal to 2 pi radian and equal to 1 revolutions. Okay, yeah, so that would be the conversion you need to know about the angles or say displacement. But in physics, which unit we prefer? Yeah, usually we prefer using the radian because radian is a unit will be considered as the dimension list. So we just write, so in physics, if you keep that in the radian, we just write that into 2 pi. So just a number. They don't have unit, right? Or you say they don't have a dimension. So usually we say radian is dimensionless. So that would be pretty easy to convert or use during the calculations. So I suggest you, so when you need to have the degree or see the angles involved in your calculations, try to convert that into the radian first. Yeah, so radian will be a good unit to use in physics. Yeah, maybe they're like little confused in my yeah, we try to keep that radians inside of degree. Okay. All right. Next, angular velocity. Well, pretty similar definition as the velocity, right? So since we have displacement, so we want to find out the yeah. So average angular velocity should be like the angular displacement, or say the change in the unit time, right? You divide by the time is used to finish that. Okay. So to find out, since angular displacement will be the angles that's traveled divided by how much time is used. So that should give you the angular, average angular velocity, right? Usually the yeah, it's defined as omega. So if you learn about the derivatives, so the instantaneous angular velocity, well, we'll just approach that time interval into 0. Yeah, we got the it's actually give you the what? It give you a functions about time, like how instantly that angular velocity change, right? All right, and the unit for the angular velocity is defined as radian per second, right? So that is why I suggest you to using radian to for the unit of the displacement. Sorry, yeah, for the angle, or say the angular displacement. Or you can also consider, since the radian is dimensionless, so I can rewrite that into 1 over s, or s to the power -1. So all of that unit will be accepted for the angular velocity. Okay. All right. I'm going to clear the notes. All right. All right. Next, it shows the Yeah, the instantaneous angular velocity, just I mentioned that, is just taking the limit of the average angular velocity, and we approach the time interval to zero, and that should give you the instantaneous angular velocity. Yeah, you can find out these are pretty much similar definitions as the linear cases. Yeah, angular acceleration we just do for the find out the change of the angular velocity in the unit time. So that give you the average angular accelerations using alpha defined. You can find that the unit also is radius per second squared, and you can also write that into 1/second squares. Yeah, so this can be right in that way as well. Okay, similarly, instantaneous accelerations that works the same way. Just alpha, yeah, it's supposed to be alpha, right? Alpha is defined as a function of time when you approach you take the limits when the time intervals approach zero, right? And we take on the right is the ratio of the change of the angular velocity in unit time. Okay. So they also meant when we assume that angular acceleration is constant, so that the instantaneous angular acceleration alpha and the average angular acceleration alpha bar are the same, right? So most of the time we studied in the AP Physics 1 levels, we assume that the angular acceleration is the constant. Yeah. Otherwise, we need to take the integrations of your functions, right? Yeah. So we already considered the angular acceleration is the constant, and based on that, we can just assume that the instantaneous accelerations and this average angular acceleration are the same. All right, keep moving. Number 7. Okay, so here it just give you a table that compare the equation of kinematics in the linear case and rotational cases, right? So you can find out it's very much like similar. So as long as you just do some like substitutions, right? So you substitute A into alpha in the rotational cases, right? And V, the speed, you replace with the angular speed, omega, right? And what else? Okay, X, okay, displacement, X, you replace with the theta, the angular displacement, right? Yeah, I think that's it. And just you can see that totally the same, just replaced by a new samples. But the t is the same. You cannot change t. Time is, yeah, it's unique in the universe. It has to be kept the same. Yeah. All right. So let's try some of the examples, like using the equation shows above to answer, let's see, the first question here, number 5. All right, you can show me your answer in the chat sections. Yeah. All right, great. Yeah, let's see. Yeah, very basic, right? So we're just using the formula shows above. All right, so initial velocity. Yeah, initially the omega naught is 0.5 radian per second, right? Okay. And we also have omega 1, the final is 0.7 radius per second. All right. The time, duration time is 2 seconds. All right. So first alpha, okay, we can use the first directly, right? This one. So alpha is omega minus omega naught over t. So very basic, 0.1 radian per second square. Okay, yeah. And second, they ask for the displacement, angular displacement, right? Yeah, we're going using that, right? So, yeah, so theta is equal to v omega naught minus omega square minus omega naught square over 2 alpha, right? You plug in 0.7 square minus 0.5 square over 2 times 0.1, and that will be in radian per second. Okay, so that should give you the answer C. All right, great. Pretty basic questions. Yeah, so this package is almost done. We just recap the fundamental knowledge, and then we do a little bit more practice later. Okay. All right, give you a few seconds to write it down if you need it. All right. Let's keep moving. Yeah, this will be the last part here. Angular variables and tangential velocity variables, sorry. Yeah, so you might need some time to like find out the connection between the tangential speed and like say tangential speed and your angular speed, right? So most likely you're going to use this one, the last two, okay? But actually is derived from the first one, right? So what is the first one? First one, you should learn that in algebra or say in geometry, right? In math, right? So it's just like arc length, right? So S is actually the length, like yeah, the displacement on the arc, right? So that is the arc length, right? Think about that case. Oops. Yeah. This one is a situation we have a circular sector, right? Have a circular sectors and we will be a part of a circle. Yeah, it should be stopped here. Okay. Yeah, I just picture this is a part of the circle, big circle. Anyways, it's very ugly circles. But yeah, a little better. Okay, so we have a theta as the central angles, right? They have a arc. The arc have a measure of theta. Okay, and they want to find out the arc length, like this part, how much longer of that arc, right? So to answer that, we're using what? So the total circumference is 2 pi r. So if you are assuming that the radius is r, so it's 2 pi r, like c equal to 2 pi, yeah, 2 pi r, right? And the run revolutions, so this the theta equal to what? 2 pi, right? And and our case, this is the for a full revolutions, but now we only have L as a part of this arc, right? So the theta is your theta, right? But we know that they should proportional to each other. So like that. So the ratio 2 pi r over L should equals to 2 pi over theta, and that should give you the answer, right? So 2 pi r over L equal to 2 pi over theta. Obviously, that theta I'm using the radian system. And you cancel out 2 pi, and it give you the L equal to R theta, right? So that is how you count, how you get this result. The first one, okay. From the first one to the rest of to either way, so you can just find out the change of assuming they have a little change delta t, right? And there will be a change of the angular displacement on the right, and also on the left they have a in the unit time they have a change of s, right? So you can find out we have a s minus s naught over delta t, and that should equal r. R is unchanged, so theta minus theta naught in the unit time. Okay, so that actually give you delta t. Sorry, is a tangential velocity equal to r time omega, right? So this is generally how you get the second. Okay, or this is a like more official way to describe that, just taking the derivative on both sides, right? If you already learn a little in the AP calculus, it should make sense to you. But obviously it's not required. Okay, so the first derivative from the first line, you got the second line, and you take the second derivative to the time, yeah, internal time, then that give you the third, yeah, the third line. But you can, if you don't learn that yet, so you can continue to consider in that way in the unit in the shorter time, like small time intervals, we consider about the change of your displacement, or say in the third line is the change of your velocity in the both cases, and they should still equals. All right, but the result is pretty useful. You need to know that, and you need to know how to use them. Yeah, I believe that it should be given the formula sheet. Yeah. All right. Then we have a very short examples at the end. Let me clear it. All right, I'll give you a minute on that, and then after this, we'll have a short break. Yeah, this one, yeah, don't need to waste too much time on that. It's pretty basic. So at point one, so the v tangential speed, you just plug in the numbers. So r1. So different between the point one and two, they should have a different radius, right? r1 time omega. So the answer is 19.5 meter per second. Yeah, and linear acceleration at that point, r1 time alpha is yeah 3.90 meter per second squared. Oops. Okay, at point two, oh, I'm using T1. Should be R2 time omega. That should give you 42.2 meter per second, and accelerations at that point. I mark from 8.45 meter per second squared. Okay, yeah, so very basic plugin should give you the answer. But yeah, this probably not the AP Physics 1 levels. Too easy. Yeah, but just using that to recap the knowledge we learned at school. All right, let's take a short break. Let's go back at 6:05. Okay. All right. Are you all back here? Okay, great. All right, great. Thank you, guys. I during the break, I got one questions here. I think I need to mention about the previous question here. Well, yes, this is pretty easy, but if you someone missed it, if you're still confused, that in the questions that the angular speed is given the revolution per second. Okay, so you need to convert that. As I mentioned, as revolutions is not a good unit to use for the angles, right? Because you still need to convert it into the meter per second. Obviously, you cannot use revolution per second as the unit for the tangential speed, right? So you still need to convert that back into here, right? So this is why I prefer, or say, is you need to convert the speed, angular speed, or say all the units related to the angle into the radians. Okay, so like this one, so 6.50 revolutions per uh, per second, right? So you need to convert that into the radian per second first. We know 1 revolution is 2 pi radian, so you can write that into 6.50 times 2 pi, 1 per second. You can just skip that radian. This is actually have a radian, right? So this is 2 pi radian. You can simply ignore that because radian is dimensionless. So yeah, so this is the way that you need to write your angular speed, and using that value, or say with the unit 1 over s, and multiply the radius. Yeah, in the first case is 3.00 meters, right? So time 3.00 meters. So that should give you, oh, meters. Yeah, you're right. So based on that, with this one, it should be 19.5 time 2 pi, right? Meter per second. Am I right this time? Any other student find out this problem? No. Feedback. Yeah. So actually, this is the good point that we need to add this to the result, right? We need to add that. So I believe the rest of it should add that to pi to the result as well. Yeah, I believe so. Right? I need to add this 2 pi to the result. For that, it should be the same, I guess. Yeah, it should be the same. Right? So yeah, don't forget about that. Yeah, actually the my answer actually skip that. It should not. Yeah, thank you. Good point. Okay. Yeah, otherwise, if you're using revolutions, it's not a real unit you need to use. Right. Any question with that? All right, let's move on. All right, I will put the mass package in the folders. Just give me a second. All right, I already uploaded. You can find out in the share this folders, but I can, yeah, I will also do the screen sharing here. All right, next package is about the rotational dynamics, right? So you can basically find out the rotational stuff and the translational stuff, the linear motion. Most of the, let's say all of the sample, or say the physical quantity is comparable, right? It's comparable to each other. Like here, we're using torque instead of force, right? To like consider how you actually change the static motions. Yeah. Some others will like show like discuss the detail, but yeah. So all of those it can be comparable to the physical quantity we learned in the translational cases, either like yeah the in the yeah linear kinematics or linear dynamics, right? So all of them is actually comparable. Okay. Starting from torque, since that torque is the tendency of a force to rotate an object among the axes, right? So only study with the force itself is not, yeah, um, it's not enough. So we need to consider and introduce a new uh, uh, quantities to describe the rotational stuff. So if we have a torque, so that can make the object rotate, right? So torque is then quantities to change the rotational uh, status of the system. You can picture in that way. Okay, so torque is defined as the, let's say the labor arm multiply the magnitude of force. If you, this one actually defined as, if you were, probably some school introduced that, probably not. So the torque obviously is vectors, right? They have a demand, they have a magnitude, they have directions, and this torque, um, oops, yeah, this vectors is defined in this way. So the first is a vector, is about your displacement, or say you can define like here. So we have a point and we have a reference point. From this point that the force act on, we have a displacement, right? And your force is another vectors going that way, and yeah, it can do the cross product of these two vectors. So officially, the torque is a result of the cross product. I'm not sure you already learned the cross product in math or not, but if you already learned that, you should know that we do the cross product two vectors, they should follow the right-hand rule, right? So starting from the first vectors and this curve to the second vectors, and your sum is pointing to the direction of your resulting vectors. So this is how you get the direction of torque. Okay. Well, so in this situations, that is the first one is go like in this one, the L is go to the right, and your force is go to up, right? And you should curve your finger 90 degree in this way, and your thumb is point out of the page. So your T is actually pointing this way, right? So actually, if you consider that happen in the one page on the two-dimensional cases, so it should be like what? It should be rotate conquer clockwise, as we define the angles. Conquer clockwise is positive, so this way we have a positive torque. Or in the previous definition is the vectors point out of the page. Okay. All right. So that is about the direction of your torque. And magnitude is very basic. So it should be this one. The magnitude is L, the magnitude of the first vectors times the magnitude of the second vectors times the sine theta. Theta will be the angle in between. Okay, the angle in between. Okay, so just like this case, if the L and the F are perpendicular, so which means that the angle between those, like here, is a right angle, is 90 degrees. So we know that the sine theta, which is sine 90, is 1. So we're just doing the product of the label arm and the F, right? So this is why it can be shortened, or say the abbreviate into that easier cases. So the torque, if you just consider about the magnitude, so the torque is just the label arm. So if you using a line of action here, go, like say your F, go through the line of actions, and from the point of the axis of rotation, and you make an extension line to the line of action. So the direct distance will be the label arm, right? Yeah, so that is the L, and using that to time the magnitude of forces, and they should give you the magnitude of the torque. Okay, so also if they are not perpendicular, we can also work the same way using that general formula. Like for instance, I have a force using another color in blue. I have a force is pointing this way. Still, this is a door, right? I drag that door in that directions. So if you want to find out the torque to act on this door, so you can still using that formula. So you should have the L, magnitude of L, time this F. They should give you the magnitude of forces. and time the sine theta. Theta will be the angle in between of that. So it is theta, right? So it should be the same equivalent way that if you consider that. But in this case, you need to consider, oh, so this is the line of actions, and your label arm have a shorter distance. So that way, right? So you can find out it's actually the same if you calculate this. This is theta, and yeah, and that will be your line of label arm, right? Okay. All right, so this is the first definition of torque. Let's clear that. All right. Next, rigid body in equilibrium. All right, so the first one we know very well. So that is actually the second Newton's law, or say the first Newton's law, right? If one object is stay there, so no, or say no change on the static motions, so we will say the net force should equal to 0, right? Otherwise, they might have a net force to change the status of the motions. Okay, but first we need to clarify that the one body, or say your object is in equilibrium, is don't need to be stopped. It can move in a constant speed, right? It can move in the, well, I should say it should move in the constant velocity, or it stop. So either way, always either way we'll say that it's in the equilibrium positions, right? Yeah. So if there's no change of the static motions, we'll see that this body or this object is in equilibrium. So if it's in equilibrium, so the both of them has to be satisfied. First one, we just mentioned that the net force act on the object has to be 0. So when you analyze with the real problem, so this actually split up into two equations. The first will be like, say, in the x directions, the net force must be 0. So it will be in the x directions. So the net force must be 0. And also in the y directions, the net force must be 0. So you can consider one direction by another. Okay, so that actually give you two equations. And the third one, we need to consider, okay, since they are in equilibrium, like a stop there or move in a constant velocity, so the net torque has to be 0 as well. Otherwise, they will, well, actually generate angular accelerations, right? Yeah, we'll discuss it later, but yeah, the torque is actually the reason can accelerate the rotation, so that we high power, right? Yeah, yeah. So if there's in equilibrium, so this one, the angular acceleration must be 0, and your torque must be 0 as well. So this really give you the third equation to put in the system. So that has to be 0. Yeah. If you are giving a question about equilibrium, you need to set up a system with that three equations. Okay. All right. First example. I believe it's pretty easy. All right. You should get an idea of that questions. Someone already got the answers. Yeah, it's 1250. The answer is 1250. Yeah, so just plug in the equations, right? Times f times sine theta, right? So should have 500 newtons times sine 30. Okay, so for the torque, the unit is Newton meters. Yeah, Newton times meters. So that will be the unit for the torque. Okay, yeah. If you write in this way, the orders of the L and F doesn't matters, but I prefer you think the L is just shows in the front. So because like the official definition for the torque is just like L time R across F, right? Yeah, so the cross product, if you change the orders, that should give you the different directions. Yeah, so L it shows in the front, but actually if you write it in this way, it doesn't matter. Excuse me. All right, so this is the first questions. I'll clear it. All right, second one, also not very hard. Oh, someone got the answer. Yes, B, right? Very basic. So you just hung the over 1 point, A, B, C, D, E, right? So make this balance each other. So think about that is, okay, so we need to make what? The net torque equal to 0, right? So since we know the mass for the two blocks is 4 kilogram and 3 kilogram. So on the other hand, they say the weight of each is the 4 to 3, right? So we need to we know that weight will be the only forces to the system, right? Yeah. So we have one force, 4G on the left. This is 4G, 4 times G, and on the right is 3G. I don't know why today's no, it's acts pretty slow. Okay, 3G. All right, so we need to find out a point. Let's say some point here, right? So we have a L1 and we have a L2. So the net torque must be 0. So the first torque from the left, torque 1, should be what? Should be L1 times 4G. 4G will be the weight of that blocks, right? And this one give you the counterclockwise rotation, so that should be a positive, right? And tau 2 will be the torque generated by the weight on the right. So it'll be L2 times 3G. Oops. Okay. And this one's rotate clockwise, so that is a negative torque. Yeah, you can picture it that way. And this two, when you sum them up, right, tau 1 plus tau 2, it should give you 0, right? It should give you 0. So the the ratio of L1 to L2 must be what? Yeah, it'll be 3 to 4. So in that case, B will be the options, right? Okay, cool. All right, great. Let's keep moving to question number 3. Yeah, so the example I selected is actually a relatively easy. I just want to help you to review all the basic idea, and then we can quickly jump into the practice test later. So hopefully we can finish up that package today, and then we'll do more practice and next time we'll do a lot of practice for all the knowledge we learned. Okay, number 3. Oh, here because like this person is held by 2 feet and 2 hands, so I'm assuming that a hand, like the forces act on each part is equals. So you might consider to divide that answer by 2. Mhm. Yeah, because the question they ask you, the normal force exerted by the force of each hand and each foot, right? Okay, I just do the free body diagram very quick. Oh, I better use the red. Okay, starting from the gravity is from the center of gravity, right? There's a formula here, mg, and you have 2. Okay, someone got it. Great. Okay, I'll say this is 2 foot, right? And there's a normal force going up, 2 hands, like this, right? Okay. Then what? Yeah, you can using that the equations, right? Obviously, that horizontally we don't care because there's no force at all. So vertically, they have a 2, let's say 2ff plus 2fh minus mg should equal to 0, right? So this comes from f the net force in the y direction must be 0, right? And the torque must be 0. So we consider what? Okay. So when you analyze with the torque, there might be a problem, right? So depending on what, which the center of rotation you selected, so that give you a different result, right? So you can use that one as the center pivot. You can use here as the center pivot, and you can use that as the center pivot, right? And how? Oh, actually, any point, can be your center period you selected. You can use that point. Yeah, you can use this point. You can use that point. You can use this point. Okay, any point is okay because it's in equilibrium, right? So while you might ask, like, which is the best point I need to select? So depends. Depend on what. So if you have a point, if you have a forces, and you don't know the magnitude, this is unknown forces. Well, because you don't want that shows in your equation because you don't know the value, right? So you better chose the point that the unknown forces go through as your the axle rotations, right? So in that way, you know that if I have a force go through the axle rotation, there's no label R, right? So which means that the torque generated by this force must be zero, right? So this is the good reason that I select that point. If we have an unknown force, and you set up the axle rotations on that force, or say your unknown forces go through the axle, the rotation. That will be the best choice. Okay, so this is um, the rule of thumb that how you select the axle rotation. Okay, like this question, we have actually two unknown forces. You can pick up any one of that. Like I can do, let's say this one. Yeah, I can select that one. Okay, so this is the point of the rotation. So in this way, we have a mg. Okay, this force going down, and we have a force going up, right? Yeah. And then we just can calculate one by one. This force, since this force goes through this the axle rotation, so they don't generate any force torque, so we don't count that. So this is TG, so plus TH equal to 0, right? So because the TF equal to 0 is we already got that. TF should be 0. So the torque generated by the foot, the normal force from the foot should be there. Okay, and this one, it should be mg, the force, or using the distance, assuming this is L1 and this is L2, right? If you're doing that way, so L1, and the force, the torque generated by the weight have a trend that is rotating clockwise, right? Clockwise, so it has to be negative. Plus L1 plus L2. Yeah, because the length is count from the axis rotation to the line of actions, right? So it's L1 and L2 times double of FH. So that should equal to 0. Okay, and you get another equations. And obviously we have the first equations, and we have a system to solve, and that should give you the answer. Yeah, the mg is given, so we only have two variables to unknown, which is fh and f, right? Yeah. And you got that fh equal to 96 meters, f equal to 196 meters. All right, I'll give you a few seconds to finish your notes. All right, let's keep moving. Next one, number 4. Okay, so still a equilibrium problem. This one I give you a little bit more time, like a 3 to 4 minutes. All right, this one I probably need a little more time on the calculations, but let's do the free body diagram altogether. Um, okay, so we have a three equation to establish. First, the net force in the x direction should be zero, right? And net force in the y direction must be zero, and that torque must be zero, right? Yeah, we just follow that rules starting from first. Okay, so doing the free body diagram first, we list the first the weight. of the ladders, weight of the ladders, okay? And weight of the person, right? So this person have a weight, P. What else? Oh, they mentioned that. So against a smooth vertical wall, which means that the wall can exert only the normal force and cannot exert a frictional force, right? So normal force, so you say that between the top of the ladder and the vertical wall, they should have a normal force. What's the direction of that normal force? Normal force always perpendicular to the surface, right? So surface is the vertical wall, which means your normal force has to be horizontal, right? So that should be your normal force pointing to the left. I'll call this P. Let's distinguish that. I'll just redraw it. Okay. All right. What else? Okay. The lower edge of the ladders, they might have another force act on the horizontal surface. Otherwise, it just slide, right? Cannot stop there, right? Cannot stand. So, but it didn't mention anything about that. Yeah, actually, they want to find it, right? So they want to find out the forces that the wall and the ground exerts on the ladder. So they should have a force from this point and point in some directions, act on this on the ladders. But I'm not sure about this. I assume that we have a force I call G. Okay, and since the direction is unknown, so we can project it in the two different directions. Like this is gy, it is a y component of this g, and some others like gx. Okay, yeah. So I think that's it. This is all the forces act on the system. So we can just using that system to get the details, right? In the x directions, we have two forces, gx and the p. So they should balance each other. So we have a gx minus p, g equal to 0. All right. In the y direction, we have totally three forces. I'm defining going up like x, y. So go up is a positive. So in that way, gy is positive, gy minus WL minus WP and then equal to 0. Okay, then what? The torque, right? We need to count the torque. Okay, so similarly, like which is your axis of rotations? Well, we have this one. We have gy, we have gx unknown, and also we have a p unknown, right? You can use either point as the axis of rotation, but I prefer using that. Why? Because if you're using that as the axis of rotation, you have two unknown forces, gy and gx. The torque generated by these two forces at 0, right? It's great. I eliminated two unknown values at the same time. So that's perfect. So I prefer to choose this point as the axis of rotation. So in that way, we only have three forces we need to consider about the torque. So first is the torque generated the WL. So we need to using, okay, so that's distance. Yeah, I'll say that is L1, and this is L2. L2, right? Sorry. Not this point. It shoots from here to the end. Yeah, this is L2. And we also need to have that distance. Because this is the line of actions, right? And to here, that will be the L3, right? So luckily that this L1, L2, L3 are kind of giving. Yeah, so we can have L1 times WL. So this generated like a clockwise rotation, so it's just negative. Similarly to WP is generate a negative rotation or torque, will be L2 times WP. And thirdly, that the P, the normal force from the wall, is positive, it can generate a positive torque. So plus L3 times P. That should give you 0, right? Clear out. All right. Use the knowledge of the track. We can get the L1. Just right on here. L1 should be, we know the length of the letters, which is 8 meters. So this is a half. So this is a 4 meters here. And that one should be 4.00 meters time. I believe it's cosine, right? I better write it here. So L1 equal to 4.00 meters times cosine 40 equal E. L2, didn't mention anything about L2. Okay, they said that this point of the person's stand to the ground is 6.3 meters, right? So 6.30 meters time, I believe it's the same cosine 50.0 meters, right? And L3, I believe is just total length of the letter, so 8.00 meters time inside of cosine has using the sine 50 here. Okay, all right. And then we have a length of each and you plug in and you should get the answer. All right, you can do it at home if you didn't finish that. So the answer for it, P is, I believe it's 727 newtons. Yeah, and I believe Gx have the same value. So Gx have the same value as P, and Gy I got is 1230 newtons. So you can just check that yourself. I believe it's, I hope it's correct. All right. Okay, I give you a short time to make notes, or you can do a screenshot. All right, let's move on. Oh, next topic here, number 3. Newton's second law for rotational motion about a fixed axis. Okay. Um, well, just like, yeah, you can consider, yeah, so this one is comparable totally to the Newton's second law, right? Equal to ma. You can compare that the net force in the Newton's law will be the net torque. And the acceleration here, linear acceleration is comparable to the angular accelerations, and the I, right, so the moment of inertia is comparable to the mass. So this also helps you to understand what is mass is. So mass is the characteristic to determine and how easy or how hard an object can be changed their original state of motion, right? So if a mass is large, it's a little bit harder to change their state of motions. Otherwise, if m is smaller, so that'll be pretty easy to change it. Similarly, if they have the system have a larger moment of inertia, that will be very hard to change the status of rotational motions, right? It will be hard to rotate, right? If the system has the relatively small motion of inertias, well, that will be easier to rotate it, right? So it'll be easily to rotate. Yeah. So that is actually a properties of your system, right? Um, yeah, so this one you can actually analyze by just from the Newton's law. So if you have like picture, we have this is a fixed axis and we have a point mass in the system, let's say m1, right? So we have a distance r1 away. So we can just using the torque and be represented as r1, just have a force going that way. Right, and time, that is time f, right? Yeah, that will be the torque generated um, by this force. Okay, and this force I can just simply consider that is ma, right? So it can be accelerated that way. So we have a one object have a force going up, and there will be accelerators of this mass going up, right? So this is ma. Yeah, and A, based on the knowledge of like the relationship between the tangential acceleration and rotational acceleration, and this A can be considered as what? We know that A is actually alpha equal to A over R. So A is actually R time alpha, right? So I can rewrite this R1 time M A is to be replaces R time alpha, right? Yeah, R1 because I'm using R1 here. So this one can be actually rewrite into M time R1 square time alpha. So this is the first part time alpha. Uh, Imagine that we have a lot a lot of M1 in your system that has been rotated all together to the same axis of rotation. So you have M1, you have M2, M2, M3, M4, right? All of that is just summarized like we sum up all of that part. So each one of them is rotate with the same accelerations. So in that way, I just need to accumulate those things all together. I just accumulate. So all the stuff together. So this one is defined as I, right? This is how the I come from, um, yeah, I time alpha. Since we believe that every item in the system is rotating with the same alpha altogether. Yeah. All right, let's just wrap it up and with this question, let's do one more question and we're just done with today's work. Let's do number 5. It's supposed to be easy. Yeah, beware of the unit. Here is still using revolutions, so you need to convert that into radian. Okay. All right. So this question, the idea is pretty basic. You just need to find out an angular acceleration first, and then they ask for what is net torque, right? So the net torque is just using the moment inertias multiply this alpha, the angular accelerations, right? So starting from the figure out the alpha. So since we know the initial angular velocity is 0, right? And the final angular velocity is given, so we can just using the formula alpha equal to omega square minus omega naught square over 2 theta, right? So we can just using that. Well, first one, the angular speed, yeah, I believe it's 80. Oops. Time 2 pi, right? Because you need to convert that into radian. Uh, 1 over s squared over 2 times 240.0 revolutions, time 2 pi again. Yeah, just that. Right. Okay. So this one should give you the answer. Yeah, I believe it's 83.8 1 per second squared, right? And then you just plug into the values. I time alpha. I is just giving here, and you just plug in. It should give you 0.118 newtons meters. Okay, yeah. very basic, but as just like the previous questions, to the angular velocity or angular accelerations, use the radian instead of revolution over degrees, right? All right, cool. Homework. Okay, I will post the new homework in this week 5 folders, but I believe most of you didn't finish the previous 2, the additional free response questions. So so later on, I said like maybe on Wednesday or Thursday, I'll post the answer of that in the folder as well. But you should using some time to work with it. Okay. And all right, any questions? All right, great. All right. Thank you for attending. So see you next time at the same time, 5 p.m. on Saturday. Okay. Bye.